Thank you for inviting me. I'm excited. I haven't been to one of these in quite a while, so it's exciting. Everyone get my pun? No? Okay, well, I was really see an O. Thank you. Somebody got my pun. Okay. Thank you guys. Yeah, so to begin with, this has been joint work sort of over the past 3 years with a bunch of different people from McGill, people from Google, etc. Have been all working on this idea. Okay, so I wanted to begin with sort of what are the challenges we sort of face in machine learning. And I stole this plot. Actually, I think this is from Damian's thing. I stole it. I should give credit. I'm sorry. It's Damian. I stole it. I'm sorry. Okay, so what are some of the challenges we face? I think the biggest thing, right, is that there's a huge gap between what is actually happening in practice versus what is actually happening in theory. Practitioners kind of ignore everything theoreticians say, or they don't really use it. Okay, we'll maybe ignore them for the moment. But as theoreticians, we're also sort of responsible for this in some ways. Why? Because as Damian has proven, you plot these great charts like this. So you have some theory. We do runs of our algorithm, which are sort of the gray lines, right? And we have sort of our theoretical thing, which is the blue line, which, by the way, usually it's not even on the same scale. And we say, oh, well, it always works better in practice. And we're always saying it always works better in practice, right? It's not just like some of the time it works, it's always better in practice. And so this, usually we just leave it at that. We say, okay, well, it's just, a difference between theory and practice. But what I want to go back and what I want to say today is maybe we should think about why we have this difference, okay? And try to answer this question of why we have this big gap happening. And what I want to sort of claim is might be one of the reasons here is that we sort of have a mismatch between what our assumptions are and what is actually happening in the theory, what's actually happening in practice. So what I mean by assumptions, we have these sort of rules which we say, well, we're going to assume convex, non-smooth, etc., right? And that's what we leave it at. That's sort of what we're taught. But maybe we need to go back and say the actual problems we're working on aren't just about smoothness and convexity. There's something more going on. Okay? So that's the goal for this. So what do I actually want to do? Okay, so if there's anything you get out of this, I hope it's this slide. So the basic idea is that I want to be able to predict the behavior of stochastic algorithms without actually ever running a stochastic algorithm. Okay, and I want to do this on real data. All right, so here is an example. This is random features with CFAR. Okay, and of course, I can't just be able to predict the behavior without knowing something about the data. So what am I going to be allowed to know? I'm going to be allowed to know things like the spectrum of it, okay? The initialization and the targets, all right? And here, what you see here, this is the empirical loss versus iterations, is that I can actually predict the behavior. So the prediction is the straight lines, okay? Those are the predictions. And on just even a single run of SGD, I can predict its behavior. Those are the squiggly lines, okay? So at each iteration, I can predict the exact curve, even on single runs, all right? By the way, please ask lots of questions, okay? Because it's going to feel probably a little different than what we've seen before. Goti, I already know what's going to ask me a question. Yes, go ahead. Yeah. Oh.
Awesome. So just a clarification on the setting. So this is linear regression with deep, deep, not that deep actually, but non-linear random features.
Yes, yes, yeah. Actually, I can apply an activation function entry-wise. So in some sense, there is some non-linearity in there. Yeah.
Yeah, non-linear random feature. Yeah. So W is random.
Yes, yes.
And sigma is whatever you want.
Yeah, yeah.
And no assumption on sigma?
It's an entry-wise activation. So it can be anything. It can be ReLU. It can be
increasing.
It doesn't need to be increasing. Usually what you need is, and we can talk more about this. Okay.
We don't need to okay.
Explain what you need. Yeah.
But that's it.
Yeah.
Thanks.
Okay, cool. Very cool. Any other questions? Now, before I go, this is optimizer, so I always have to say something. I'm also an optimizer. My goal isn't actually to use this in replacement of running SGD. Okay. The point is that I want to be able to predict to remove some of the problems that we have when we analyze SGD, for instance, the randomness, so that I can actually use this prediction to actually improve the algorithm itself. Okay, so it gets information about step sizes, learning rates, all sorts of things. Okay, that's the idea. Because actually generating this curve is more expensive than running the algorithm, right? You have to know the spectrum. Cool. All right, so what do typical machine learning problems and what am my claim about assumptions here? Well, my claim is that these types of problems tend to be what I call high dimensional. So that means we have both a large number of features D, so the space that we're minimizing over, as well as a large number of samples. Okay, so we have features and samples are large. Now, the other assumption, which is maybe not as super common, but is starting to become more well known, is that we're not in classical statistics settings. So classical statistics would say you fix the number of features and you let sample size grow. Okay, that gives you different behavior. What we're seeing here is that if we plot sort of parameters over data points and we look at the state-of-the-art models, that we have a tendency that they're going proportionally to each other. So that means in some sense that the number of samples and parameters are growing they're both getting big, but they're growing at the same rate with each other. Okay, this leads to very, very different dynamics than what you have in classical statistics. Fix D, let N go, that's classic. This is where we're assuming sort of a proportionality between N and D. Okay, so what really makes high dimensions very different? So the main difference is that your input, which can generate your worst case complexity, is really, really far from the typical one. Okay? And so you might say, how do you actually capture high dimensional structure? Well, the classical way of doing this is to put some sort of probability distribution on your inputs. All right. I will remark that some of the things I will talk about will have deterministic designs, so you don't actually need the probability distribution. Okay. And this idea has been well studied by lots and lots of different people. It's related to average case complexity, etc. Okay. So this goes to a little bit of what Gautier's question is. I wanted to create sort of like the way we think in optimization, a class of functions that we can work with. So here I'm going to make this high dimensional sort of class of functions. I'm going to assume that my data for the moment is coming from some normal distribution with some covariance K. I can allow my covariance to be basically anything I want. Okay, it just needs an operator norm which is bounded. Okay. And I'm going to assume here D is large. So my A is going to be generated from RD. It's going to be very large. Okay. And the idea here is that I have this function F where I'm taking it's going to be, F is going to be low dimensional. So what I mean is you take a high dimensional A and you hit it with an X, which sort of makes it low dimensional. Okay. And then you apply some low dimensional function. So F here is always kind of low dimensional. You see? All right. So what does this allow? It allows you to study things like GLMs. It allows you to study multi-index models. So you can do things like logistic regression, multi-class. Here your M would be, say, the number of classes. And as X star here, it just is sort of allowing me more flexibility in my model. So it can either represent something like a ground truth signal. You could have it be your mean of your data, or just in general, some fixed vector. Okay, just to allow a little bit more flexibility. Okay, so I'm going to first start by studying streaming or one-pass SGD. So what's the idea here is that we're going to generate at each iteration a new data point, okay, and update our gradient based off of a stochastic gradient on the data point. And what we see is something maybe surprising for some people, is that when you let the number of parameters in samples grow large and simultaneously, what you can show is that the risk evaluated at SGD will actually concentrate around a deterministic function. Okay, you can analyze this smooth function, and it's completely determined by the covariance in K. And that's what you're actually seeing here. This is KL, the logistic. So this is your loss, and these are SGD iterations. And what I'm doing is I'm just generating many samples, many runs of my algorithm, and I'm just plotting the variance. Okay, and then I'm making the size grow larger and larger and larger. And what you can see is that over time, the variance is shrinking, and you're getting concentration around this red curve, okay, which we hope to predict. Excuse me. So why do we expect such a thing? Well, this high-dimensional composite structure is basically enabling some sort of extra averaging effect. So when you hit a high-dimensional vector with an x, you're averaging in some ways. So you expect some sort of concentration, some central limit theorem just from that effect itself. This is already on top of the extra averaging from the expectation. The other thing which might be more surprising, I don't know how many people see this, is that lots and lots of statistics that we're interested in analyzing take a specific form. So if I form this W matrix, which is formed by taking sort of concatenating my iterate X with X star, okay? Lots of statistics will actually look like the form a function, low-dimensional function G, composed with this matrix W transpose Q of KW, where Q is just a polynomial. Okay, so what do I mean by this? It creates this like 2x2 block structure, the matrix. So what are examples of this? Because of the composite structure, the risk has this form, the gradient squared. Any kind of distance to optimality also takes this form. So just to make sure we're all on the same page, because it is a little weird to think of this, let's look at least squares. So if we take a least squares problem, it looks like some trace of like A transpose X minus sort of B squared. Well, we can represent it by taking out the expectations. When you do all the expectations out, you get a K that appears. So there you see your X transpose KX is there. Okay. Maybe more surprisingly, you can do this sort of structure with like logistic regression. So here I've written down what logistic regression would be. Okay, why do we get, maybe not so obvious, why you end up with something which looks like some X transpose KX appearing, but you get it because if you look at X transpose X, it has to be a normally distributed random variable with variance X transpose KX. And then if you look at the covariance between these two, it's giving you X transpose KX star. And okay with that? Okay. You can also do some things with simple two-layer linear neural networks. Okay. Also fit this form. And it's simply because every time you take X transpose A transpose X, you're getting something which is normally distributed with the correct covariance given by like X transpose KX. All right. Okay. Yeah.
So for all this work, we need to keep n x compared to d, which is
Yeah. Yeah.
that's very important.
It is really important. So you can actually allow M a little bit to grow in D. It can't be totally proportional. So I don't quite know how to do it. And it's a great open question to study exactly that. It's doable in some ways. Just
right, it's reasonable to assume m fixed because it's like number of Weber and stuff, but yeah, okay.
Yeah. The thing which is kind of funny here that this is going to be sort of finite dimensional. So the results will hold for D and M, right? And so you can push the M to be on your problem the same order as D because it's finite, but that's a cheat. So I agree. It'd be nice to do the whole dynamics in that case. Yeah.
Can you go back to the previous
Yeah.
slide? I'm not sure I see second one. Because the function G has to be outside of the expectation, and here the expectation is.
Yeah. So when you take you would take when you do this A transpose, so when you know A transpose X has this covariance, you can represent it by some W, which is square root of this, or you can represent A transpose X as equal to the square root of this times some W, which is normal identity covariance.
Yeah.
And then that way you can replace the expectation with a W, which is just some function integral because it's over some normally distributed. That becomes your G. I can write it down.
Yes.
Yeah, it's a little trick, right? Cool. Any other questions? Have I lost everyone? Okay. Getting your probability on. Old school probability. Okay, so basically lots of things that we're interested in actually take the specific form of these statistics for polynomials in Q. Now the problem is that we need this for every polynomial in Q. So we need every Q, okay? Now every Q is a problem because it's too large, and I will explain a little bit later on why you need every Q. So we have to use a trick to reduce, like, all polynomials are too much to deal with. We need something like that we can actually handle in the to analyze. So what the trick here is that we use something called the resolvent. So the resolvent of a matrix K is just Z minus K inverse. Okay. And Z here is a element of the complex plane. And if you see this, you might have seen this if you took complex analysis many years ago, but there's a way to recover any polynomial by knowledge of this resolvent by just doing contour integration over it. Okay. So in some sense, this is like encoding all polynomial information. Now, the way you think about it, it's encoding all moments of K. It's another way. Yeah.
Quick question about. Yeah, thank you, Gauthier. So to recover the Q, it's just you need a specific path in the complex plane, and given a path, well, each path in the complex plane leads to a specific polynomial.
Yeah.
Correct.
Gamma, your contour, just needs to enclose the spectrum of K.
Okay.
So any gamma which encloses the spectrum of K from complex analysis gives you that it has to, this is Cauchy's integral formula.
Okay. So gamma is linked to the spectrum of K. Okay, so thank you for the clarification.
So if you in finite, by the way, you can just think of if you have finite spectrum, then you would just do a contour around each.
Okay.
And then yeah.
All right, thank you.
No, it's a great question. Cool. All right, so what is the main result? Well, basically what we showed is that all we need to know is the dynamics of this resolvent, this form, W transpose R W. Okay, so to do this, first I'm going to create a continuous time scale. So what this just means is that K iterations of SGD is going to be equal to T times D, where T is going to be my continuous parameter. Okay, and what you show is exactly what you want. That this S applied to SGD will concentrate around a deterministic function. And then because all your statistics can be determined by this deterministic, this S matrix, you can recover any statistic of it. That any statistic under SGD will concentrate around a deterministic function. Okay. The idea here is that this deterministic function for S will be defined by some closed formulas from closed ODEs, and you can get the statistic just by doing the contour integration. Okay, very nice. Actually, we'll see a little bit more about this too. Okay, so how do we do this? So the way we wanted to do this, or what we were interested in, is to create another process, which is like SGD, but in continuous time so that we can use calculus. Okay, so we're going to create a diffusion process, but this is not the diffusion process that you probably learned about when you did SGD. So this is not stochastic approximation. This diffusion process is not created by creating a continuous time by sending step size to 0. It's done by discretizing using the fact that you have high dimensions. So you're discretizing your time by dimension, not step size. Why do I care? I care because I want to keep my step size large because I want to analyze this dynamic so that I can actually gain information about gamma. If I can't, then I have to send the step size to 0 and I lose sort of that information. So it's created, again, the continuous time process is created by dimension. So time equals 1 corresponds to doing T over D iteration. Okay? Is that clear? The other thing you have to do, and this is also a cool thing where you can do using dimensionality, is generally when you create your new process, you try to make it so that the mean and covariance of SGD match up. Okay? The idea here is actually we don't need that. That's like a little too strong. Why is it too strong? Because usually the covariance is really, really hard to actually work with. So if we actually want to work with something, and our goal really isn't to create two matching processes, like we're only interested in looking at statistics under those processes, then we can reduce the covariance in some way using dimensionality, using averaging, so that we still get that statistics under the two processes are the same. Okay? So this is where we're really using dimensionality to sort of help us reduce the difficulty of analyzing SGD. And indeed, you can prove that. You can prove that this process is the high dimensional equivalent of SGD. That is, any statistic under SGD will concentrate around a statistic under this process. Any questions? All right. Okay, so how do we get our determinant? Oh, yeah, go ahead.
Some, let's say, just to take some time to think about these results. If you go back,
Yeah.
So in you only cover the case D equals N, or you cover the case with different ratio for, because so you say that K is equals to TD.
Yeah.
Then you say that T equals 1 means N SGD update.
Sorry, did I have an N here? Yeah, so this should be D SGD.
Okay, so it should be D.
Yeah.
And because D and N goes to plus infinity, do they go as fast, or is there a there is a constant that's
so they're proportional to each other because this is one pass. So if you think of N number of samples, you can't repeat in this example. When we do we'll do a repeating version of it, and we'll still need the D over N is roughly proportional, both going to infinity simultaneously.
And roughly proportional is like you don't exactly need them to be proportional, but you need the ratio to be bounded.
So in some cases, you can get away with like N or growing a little bit, like you can get away with these things growing a little bit faster than each other, but you can't you can't have them grow one grow exponentially faster than the other. That makes sense.
Okay.
Yeah. You can get like a little bit of a log or yeah. Great question. Cool. Anything else? Okay. We're going to get our EDO calculus on. Everyone ready for calculus? Okay, so what's the point of all this? Well, how do we actually construct the deterministic equivalent? Well, we know we have this like diffusion process, which we make continuous time. And the reason you make these things continuous time is because you can do calculus. So let's just do calculus off of this. Okay, so we have this homogenized SGD. We can apply calculus. We get an EDO, we just do EDO calculus. Now, when you do EDO calculus, you always get like an extra term. I don't know if everyone remembers, it's an extra term. And that extra term is exactly corresponding to SGD noise. So you have an exact formula for what happens to SGD noise, okay, under statistics. And then the first term is just sort of what you get when you do gradient flow behavior. Okay, you also get this extra term, which is some sort of martingale. It's the Brownian motion part of it. Okay, but what you can look at if you wrote everything down and you stare at it, you can actually see that the first two parts are actually all just a function of that S matrix. Okay, so all of this is some function of this S matrix. So you could say, well, why don't I just let phi be S? And then I close in the system, right? Because then I do EDO, I get that ds is equal to some function of s plus some Brownian motion, which you show goes to 0 as dimension gets large, okay? And so you say, well, to create my deterministic equivalent, I'll just drop that Brownian motion part. And you just say, I'm just going to make my deterministic function for S be the solution to that ODE. Okay? And then from that, you can get your statistics, right? So you have D of S is like G of S. Now you just replace those with your deterministic equivalent. Then you say, well, any other statistic was like F of S. So I'll just replace the S with my deterministic one, and it works. That's actually how you get it. Kind of nice, right? Kind of pretty. So that's actually how you get your deterministic equivalent. And that gives you your theorem closeness of everything, that you can write everything as an ODE. Phi of SGD is equal to phi of under this diffusion. Then phi under this diffusion will concentrate around a deterministic process. And you have a formula for everything through this S. Very cool, right? You also have a formula for how SGD noise appears. You have an exact behavior of it. Okay. So I just wanted to bring up why the resolvent is so important. Okay, so let's look at the least squares problem. And let's suppose we actually, I said like, oh, we only needed like X transpose KX, right? It's the only thing that appears in the loss. So if you do Ito calculus on this, what you get, just look at the first term. If I just assumed I only needed X transpose KX to write down the loss, well, if you write it down, you get this extra K squared appearing. And it's because you get an extra one from grad R that appears, pops out, right? Okay, so now you have like X transpose KX, X transpose K squared X. That's a problem because if I wanted to close this, then I would need to know X transpose K squared X, etc. Okay, so that's why it doesn't quite work. But why does the resolvent have it? So if you did the same thing with the resolvent, you would still get like a KR. But the nice thing about resolvents is that there's identities exactly made to handle this. So if you had like KR, you just add and subtract Z. Because this is equal to an inverse, they cancel and you get identity plus resolvent back again. So that's why the resolvent is a nice thing that closes under derivatives and things like that. Okay, if there's anything you learn, go back to complex analysis and remember resolvent. They're super useful. Okay. That's why you need the resolvent. All right, so I'll pause for a moment. Is there any other questions? Have I lost everyone?
Yeah, just to understand, so can you go 2 slides before?
Yeah.
So just to understand steps. So first you start with determining the quantity phi of x. Then from this you connect it to a stochastic differential equation. And then you said, oh, the stochastic differential equation phi of calligraphic x. Actually, I can just drop the stochastic term. I just keep the phi, which is deterministic. And then you have like that chain of events saying, oh, there is this one which is close to each other. Second equation, they are close to each other. Therefore, I can use phi of t to estimate my statistics. Is that correct?
That's right.
Okay, just wanted to be sure. That's true. Thank you.
Yeah, and the other thing is that the diffusion process is not the classic one. So you have to do prior step to constructing the diffusion is you need to do a reduction in the diffusion coefficient. That's where you use like averaging dimensionality reductions. It's all about reducing the diffusion coefficient. Cool. Any other questions? Okay. So now you guys might be saying like, why care? Like, what does this tell you? Why is this interesting? I just compute some deterministic dynamics. I have to solve some ODE instead. That seems just as hard, right? Okay, so why do we care? Well, now we can start to go back and think about questions that we want to know about optimization. And instead, we can just say, instead of using the stochastic process stuff, let's use the deterministic equivalent. This deterministic function instead. So for instance, you might say, oh, natural question, what learning rate should I choose to decrease my distance to optimality at each iteration? Okay, well, we know we can't do this because of SGD. We directly look at SGD because it has a noise, right? Okay, so we can't do that. Instead, we could say, why don't we use this deterministic equivalent instead? It's a continuous function, or it's a deterministic function. We could just say, when is that thing monotonically decreasing? Okay, and so you can do that. So here I'm letting the script D be the deterministic equivalent of the distance to optimality. You can write down, just apply EDO calculus, and you have an expression for what everything is, right? And then you can just say, well, what happens if I want to make sure that this quantity decreases at each iteration? Well, I just need that D of it is less than 0, right? Well, you just solve that, and you get a formula precisely for the step size that decreases at each iteration. I didn't need to use distance to optimality. I could have used risk. It doesn't matter. You could do the same analysis, and you get a different equation here. Okay. So what's interesting about this is that these A and I's, they just come from expectations over little f. So they tend to be, they're low dimensional. Okay? They don't carry K and D in them. They come from f, little f things. All right? When you have like bounds on your function, like convexity and smoothness of f, you can actually lower bound these quantities. Okay? So in the case of least squares, the lower bound is q is actually 1. And that leads to this sort of 2 over the average eigenvalue behavior. Okay. The other thing you see is that the average eigenvalue is playing a much, much larger role here. Okay, so the average eigenvalue of your K, your covariance, is actually playing way more of a role than the largest eigenvalue. So average eigenvalue is explicitly presented here. Okay.
Question for you, Courtney.
Yeah. Yeah.
So this critical step size, this is not the best one. This is the one that is the, as you said, it's like the last point. So if you're larger, you diverge.
Yeah.
So
Yeah.
you want something that is smaller than the critical step size, maybe, because
Exactly.
it's not clear that the critical step size is like
it's not the optimal.
Okay.
It's actually like the upper bound. It's like a stability. It would be like what we would think of an optimization as stability. Like you would want to decrease. It's not optimal.
And so what about, can you use the same technique to minimize the different
You can.
D of D square?
It's also not optimal. Even if you minimize you could minimize the right hand side and you would get an expression, which also works. It's not optimal step size in the sense that it's only making sure that at your next iteration you decrease by the max. So it's not saying over the course of the time it is, but it does do well. I just was playing around with it. It works pretty well. Yeah.
Another more conceptual question.
Yeah.
So this critical step size, without your lower bound on A and I, depends on T, which, okay. But on Z, is like, what is Z here?
Yeah, so it's a little bit hidden. You can represent this as expectations over F, and so it removes the Z. The Z was this contour integral. So there's another representation via the expectations. So you can imagine that you could sample A and I via this other representation. This comes from the EDO calculus representation of it, the diffusion version of it. So the S is, the Z is hidden because you do another way of thinking, you do a contour integral to remove the Z.
So it doesn't depend.
It doesn't depend on
So
Z.
it doesn't
You
depend.
should not have a Z there. Yes. Yeah.
I see. So you can compute it given a Z, but for any Z, it's the same value.
Yeah.
Thanks to some
Contour integration. Exactly. Trick. Yeah.
Okay.
Yeah. That's exactly
So
right.
the only variable that changes is T.
Exactly.
You have a different critical step size for different times.
Yeah, and it's represented as expectation, so you can sample if you wanted to as you go along. Yeah. A way to think of this critical thing is potentially like it's a metric to check when you're getting a bad step size. So if you use something like a fixed step size, as you're going along, you can actually sample this quantity, get an estimate of what it should be, and use it to say, oh, I'm getting close to a point where maybe I should decrease my step size. So, yeah.
But we know, like with deep learning, that actually, even if you increase the step size, the curvature of the landscape may change. So this is true under your assumption of 2-layer.
Well, this also adjusts, right? So this is changing in time. So when you take a step, this will also change the critical, right? It adjusts automatically.
As a function of your current X.
Yes,
I see.
yeah. So it does the correct adjustment. Yeah. Everyone okay? Have I convinced you that this is not such a bad idea? Okay. Okay, it leads to some cool things. Okay, so one thing you can immediately get is things about like convergence rates of stuff, like distance to optimality. You get the classic, you get a better result as you get like the average condition number is actually playing a specific role here, not the largest one. And again, the average conditioning is average condition number, average eigenvalue is really, really important in these things. Okay, it's not the largest at all, right? Cool. All right, just to show you that this works, it's kind of cool. You can play around with different covariances. So here what I'm doing is I'm running logistic, okay? I'm doing sort of a covariant, I'm changing my covariance so that I'm fixing the average eigenvalue, and I'm allowing the largest eigenvalue to vary. And what you see here is if you plotted that critical value, as you vary the learning rates, and I'm just plotting the last iterate, you see that they all sort of reach the same value, and that's because the average eigenvalue is fixed to be the same. So this is just to show you that average eigenvalue is really playing the key role in all of this, not the largest eigenvalue, okay? And the trace of K is something you can actually find in practice. Okay. Any other questions? So there's a lot you can do with it. I haven't explored it all. But I see Gauthier wants to ask another question. Okay. Okay.
I was ready to give
Okay.
to someone.
Okay. Any other questions? Okay. Have I lost everyone? Seriously, ask me if I've lost everyone. I tried. This is a lot of things. Yeah.
Can you just repeat where like the average eigenvalue like comes into play?
Yeah. Why is it playing a role? It actually has to do with it's all the way back, but actually this SGD noise, term is really hiding that there's some average eigenvalue. When you actually write down what this is, it's actually the average eigenvalue, which is appearing there. I know it doesn't look like it in this form, but when you plug it in with like a phi and like a grad f, you'll see that it actually is the average eigenvalue. So that's where it's coming from.
So for people who are not used to optimization, maybe we can dissect. Because usually what you have in multiply by gamma square is the worst case eigenvalue.
Yeah. Yeah.
And like in that case, because you have the average, you end up like conceptually replacing the worst eigenvalue by the average one.
Yeah. Usually in practice, your average eigenvalue is much, much smaller than your largest one. Usually the largest one, there's like an outlier related to it. And so this is just showing this. And it's something you kind of expect because of SGD has a lot of averaging. You don't really care about the largest eigenvalue so much as the average should play more roles. Another way of thinking it too is that what SGD noise is doing is, unlike gradient descent sort of takes a step and it like changes the largest eigenvalue direction a lot, so the eigenvector corresponding to that. What SGD noise does is it actually spreads it all out. So the SGD noise does not, when it hits it, it like gives a little bit to every single eigenvector, not just to one direction. That's the main difference here. So average is playing roles in there. That's how SGD noise works. It's like spreads things out, which is very different than our ideas from the other things. Cool. Any other questions? Sorry, now I have to skip ahead. Yeah.
Just wondering a quick question about like the fact that it's spread out. Is it because you are assuming that the noise is Gaussian here? So
No.
if you have a structure and the noise, it still applies?
Yeah, even with structure, because the covariance, you can embed a lot of the structure into it. So it will, and you'll see in here, it has a tendency to spread things out. That's just what SGD noise is doing. It's like it like hits every sort of coordinate equally.
Okay, it will spread it out across all eigenvalues, not necessarily a subset of. Okay, cool.
Yeah, it spreads it out to all, exactly. Yeah. That's the way you should think of SGD noise. So it's like a very different feature than what you think of in gradient descent, where, you know, it's really trying to go in one direction or one area. That's why edge stability should be very different for SGD. Has to be. Cool. Other questions? More questions.
Can
Okay.
you just repeat the main takeaway from the graph you showed?
Yeah, I guess this is just showing you that. So here I'm allowed to, like, this is the graph you're talking about. I can vary the average or vary the max eigenvalue while fixing the average. And so this is really showing you average is what's dictating at least like a stability, like when you should decrease. Here it does affect sometimes your convergence and stuff properties, but it doesn't actually affect like how like when you get close to being unstable. Like, that makes sense. Cool. All right. So that was all streaming. Okay. I'm going to do another type of SGD, one that's probably the one that you guys are most familiar with, but I'm going to focus on least squares. Hopefully I have time. The idea here is that I'm going to look at minimizing just AX minus B norm squared. Okay. And I'm going to do now multi-pass SGD. So what this is what you guys were told back when you first learned SGD, which is that at each iteration you generate an index and you choose F and you use that. So why is this different? This is different because now I'm reusing my data. Okay, so each iteration I'm going to reuse, I can have a chance of reusing data. Surprisingly, everything still works out. So as you make large models, the loss evaluated under SGD will concentrate around some deterministic smooth function, even when you're reusing things. It's completely determined by the Hessian, the spectrum of the Hessian, and it's actually analyzable. And you see a similar picture, even with reusing data. Okay, well, this means you have very weird covariance structures being built up over time. That's the other way of imagining it. Here you can remove Gaussian assumptions. So these are questions I think people were asking earlier. You can allow your D and N to not necessarily be proportional. They can grow sort of polynomial. Okay, I can't do exponential, that's a problem. And I can remove the Gaussian assumption. What I need to assume is something called delocalization of the eigenvector. Now, you probably haven't heard of this. This is more from a random matrix. But what does delocalization of an eigenvector mean? It means that you don't have eigenvectors which have concentrations along coordinate axes. Doesn't need to be coordinate, but there's not a lot of concentration. Your eigenvectors are spread out. Now you might be like, why is this, like, where did this come from? Well, the first thing is that if you use entries of your matrix to be Aij, to be normally distributed, then we know if we form the matrix AA transpose that their eigenvectors lie uniformly on a sphere. So, like, that's the normal version of it. But it actually turns out that, like, for large matrices, that this property is actually universal. Universal means that most your generic, like anyone that you could probably come up with, it satisfies delocalization of the eigenvectors. You have to have very like structured random matrices to have it. Okay. So, and you can, by the way, represent this via there's formulas that random matrix theorists prove that characterize delocalization. And just to give you more examples, for instance, any sample covariance matrix satisfy this, provided that your covariance is on the feature side. So random features has this property, so you can take any activation function, entry-wise applied to two random matrices, it will also satisfy this. This is like law of large numbers, central limit theorems for random matrices. And it turns out lots and lots of random matrices satisfy. This is like their law of large numbers. behavior. They have a delocalization of eigenvectors. Thank goodness that random matrices have studied this problem, so they helped us. You can prove a very similar result. You can prove a homogenization result. So first you can prove homogenized SGD, that there is a diffusion. Here, if you notice, this is exactly the same as the other thing. You just replace everything with the empirical loss and empirical covariance. That's all it was. You could do the exact same analysis and just replace all these with the empirical loss, empirical covariance. And here I'm reusing data. That's amazing. And you get the same conclusion that for any statistic, you have the statistic agrees with the diffusion and the diffusion agrees with the deterministic in just the same manner as before. Okay? You can actually do something more. You can actually write down exactly what the loss looks like. The loss in this case is actually represented by a Voltaire equation. So the deterministic function will actually be a Voltaire equation where the first term is just your loss under gradient flow, plus a term which is actually what SGD does, okay, to the loss. It creates this mixing term. That's what I was saying. You can look at what that mixing term is. It's involving the eigenvalues of A transpose, and it's really spreading things out. What it's doing. It's really spreading all the terms out. Okay, but here's exactly what SGD noise does. You have a formula for it. Okay, for any eigenvalues of A transpose. You can analyze this thing. So for instance, you could ask questions like, well, when does this one remain bounded? If you show the deterministic function remains bounded, if and only if, you can write down a formula for its step size, just like before. Okay. The other thing you can do now is you can compare this to what happens under expected risk. So what I mean by this is that I can generate xk using my SGD iterate where I reuse my data, and I can plot my generalization. And I have a deterministic function for that. And you can look at the comparisons, and you can start to ask questions like, well, how much data, when should I reuse data? When should I not reuse data? This relates to compute questions. Okay, so what I have here is the streaming version. In streaming, if I reach a certain number of data points, I have to stop. Those are what those dashed lines are. And the not dashed lines, those are the deterministic things where I reuse my data. And you can see that for some of them, reusing data is beneficial. And then at some point it switches. And you can actually analyze this exactly. These are deterministic curves. So you can actually analyze exactly when the switch occurs. Okay. So when do you reuse? Okay. Yeah.
Just to understand the legend.
Yeah.
The streaming SGD is in green here.
Yeah.
But so the dotted line are
so streaming would be you could run, we have infinite data. If you only say have 2,000 data points, you would stop
so
at
the
that
dotted
point.
line corresponds to stopping.
Exactly. You stop at that point. But if you use multipath, you can see the top line, you actually go down. You beat it. This is unexpected risk.
So the trade-off is you go with streaming, you go faster to 0, but you go lower.
Well, it's
less slow. So.
Yeah, it switches at some point. So for the first time using multipath, when you have 2,000 data points, beats it. So reusing the data will beat it. But as you go down, eventually those two dashed lines switch over. And so at some point, there's a trade-off between how much data you have and when should you start just doing streaming versus when should you actually reuse your data.
But okay, and maybe last question. Why is the green curve going faster than your dark blue, for instance? When you stop at 2000?
Yeah, so why is this still? Because go ahead, sir.
So if you do streaming, basically you follow the green and you stop, for instance, let's say you stop at 2000. So so why are you going faster? Why do why the green is always below? I guess my question.
Yeah, it's because the green is actually minimizing exactly that function that risk. So when you do streaming, you're actually exactly minimizing the expected risk. But in multipass, you're minimizing the empirical, reusing also data. So it has to always be, in some sense, worse.
Because you end up resampling examples that make you lose like
Exactly, yeah. Yeah, but it's kind of weird that like various data point levels that you switch over, which is related to compute trade-off. So, and you can compute all this stuff because you have these deterministic curves. Yeah. And we haven't done an analysis of this stuff yet. So if people are interested in that, we can. The other thing, yeah.
So it's related to Gautier's question actually.
Yeah.
So I understand why it's going below after we pass the resampling thing.
Yeah.
But I would expect that all the curve would be the same before using again the samples. So why there is a discrepancy? For instance, if we look at the dark blue line and the green line, I would expect the both to be the same before 2000, and then they separate after 2000. So why this discrepancy before 2000?
That's the multipass is because you could have reused a different sample. So you're not using distinct samples up until 2000, even in multipass, right? You could have reused the
Oh, okay. Okay, it's not like cycling.
exactly. Yeah.
Oh, okay,
Yeah,
okay.
so this is really like trade-off of when
I
do you use, like when should you reuse data versus when should you not reuse data.
Okay, so it's because you may have used like several times the same sample before.
Exactly.
Okay, I see.
Exactly. Yeah, it really is reusing data there. It's kind of a neat thing to see the effect, and you can deterministically produce these. Yeah, great question. So the other thing I want to point out is that what I've done so far is I've just chosen a single index, or I've chosen a single data point. And I just want to point out that if you do batching, you should expect different dynamical behaviors. Okay? So if you see a theorem which doesn't have a distinction between batching and single and like small batch and large batch, you should say that the theorem is worthless because they're totally different dynamic behaviors. Okay? Like you have to take into account batching, and the results have to depend on the batching, hands down. So where do you actually get the distinction in batching? So what batching is actually where there's like a distinction in dynamics. You can actually see when your batch size is proportional to the number of samples. So what I mean by that is like you always take half of your number of samples, or a fourth of your number of samples. If your batch size is small relative to n, then you're in the small batch SGD. When it's like half of n or fourth of your sample size, you're in the large batch, and you get different behavior. And there's actually a very clear distinction between those two. So this is doing, yeah. Yeah. It's so in this case, it really occurs at the proportional batch. So log n would be considered then the small batch because it goes to 0 as a function of, yeah. It's a great question. In this setting, in practice, you might, because of the way you do batching, it might be considered large, but just pointing out that it needs to be a distinction. And I might be running out of time. I'm really sorry. All I just want to say is you can do the exact same analysis. You get for multi-pass with SGD with batching. Now you actually see the effect of batching. All it does is it replaces these things with sums instead you had integrals before. Okay, and your loss is now the loss evaluated at the full batch gradient descent, or full batch whatever algorithm you want, but with a scaled step size. That's the only difference. What's nice about this is you can actually write down optimal parameters. So you can write down what the optimal parameters for your step size and your momentum in terms of batch fraction. So the zeta here, the batch fraction, the proportionality, okay? And you can plot it for every batch fraction, every gamma, every momentum. You have deterministic things. Okay, I have 5 minutes. Yeah, that's perfect. Okay, So what you can do is actually look at a convergence rates, and what you see is the effect of what batch does. So here what I'm going to look at is like implicit conditioning ratio, which is the average over the square root. And what you can see is when your batch fraction is actually bigger than this quantity, okay, then you get acceleration in momentum. You get the square root of kappa. When it's less, you just get behavior which looks like SGD behavior. So what this means is that there's this critical batch or a saturating batch effect, which is that basically after adding more to it, it doesn't actually change your behavior of your algorithm. Like the convergence rate is the same. And you actually can see it. It works on real data. You can vary the batch. You see this is a plot of the last iterate. The gray dot is actually the implicit conditioning ratio, or the saturating batch. And you see that when you're less than this saturating batch, you decrease your last iterate, and once you're bigger, it doesn't change very much because you reach saturation. You don't need to add more to your batch. It's not going to help you anymore. And it's exactly given by basically this average condition over square root. Kind of a nice little factor. And so I will end here. So these are all the works, and I'm happy to answer questions. There's lots to do in this area. So thank you.
All right, so time for questions. So you can raise your hand. I will give you the microphone.
Thanks. Yeah, I had a question. Do you have so basically, all of this assumes like your reached regime where N and D are big enough that
Yeah.
that's your deterministic. What affects the constant like of the like in front of the convergence? Like how quickly do you reach that deterministic regime, and what in your problem affects how quickly you reach that?
Yeah, it's a good question. Okay, so first of all, you have like a central limiting effect. So it's like d to the minus 1/2 is the variance. So that's the that's the answer. It's literally central limit theorem that you prove.
But for a given D, like I'm assuming it's not just D to the 1.
Yeah, so there's a couple other things. So the covariance is in there. So sort of the operator norm of the covariance will affect your how fast things are. And then also a little bit in the number of iterations, the effect of like if you're running it for a really, really long time. Yeah.
Other questions? Otherwise, I have one.
Yeah.
So I know also it's quite important to have averaging to converge toward that star. And I don't know if you consider averaging also in your framework.
So sorry.
Using the step size of averaging like the iterates. So can you consider also that on top of everything else, or it's like included with the momentum?
You can, but these hold for last iterates. So you don't even need to do the averaging, and you get an effect. The averaging, I think, is really just because of low dimensionality properties. Like with high dimensional, you have so much averaging going on because of the inside function. You're taking expectations, and SGD has noise that you don't even need it, which is kind of what we see in practice anyway. Yeah.
Okay, so that means that in high dimensional reason, because the dimension is assumed to go to infinity, where everything becomes deterministic, and therefore you don't need averaging.
Yeah, and everything, there's like bunches of averaging occurring throughout the process. Like function is an average. You have this A transpose X, which is averaging some sort of, vector high dimension. So there's a bunch of averaging going on.
All right. Other questions?
Let's say I'm a practitioner and I want to train, my deep learning models.
Yeah.
Let's say I have a huge data set, like millions of examples.
Yeah.
Should I guess your helps answering the questions, should I use streaming? Meaning not resample or resample the data. So what I seem to understand is like we shouldn't. We should like Because this is kind of the green versus, if I cannot afford more than one pass of the data, I should just not do resampling.
I mean, it depends on sort of the number of samples, right? It's a little bit funky, right? You see in that plot, I didn't have it, but it depends on like relative sample size. So if
But-
you don't have enough samples, then reusing data is beneficial.
If
And
I have 1 billion, I mean, like 1 trillion of samples.
yeah, but it's a little bit hard because this is like on Gaussian, so it also depends on the covariance structure when the trade-off occurs.
Okay.
Yeah, but it leads to a good question. If you have enough samples, you shouldn't need to reuse. Yeah,
Okay.
which is sort of what you expect. So yeah.
And should I use large or small patches?
That I don't know. Yeah, I mean, okay, now you're really getting into compute questions. Yeah, I don't know. You have to analyze. You have to write down the formulas for it, for what happened.
But let's say my compute budget is way below the number of samples I have. So I'm on
Okay.
the left. Like,
Yeah. Probably. Okay, I can't say for large or small, but definitely reusing your data is going to be easier. Well, I guess you can't use compute. I don't know. I didn't check
Yeah.
this. I didn't look at that. It's a great question. Yeah. Okay.
Agora and Mila. So we're gonna have the figure to have Sha, who is gonna present his work on normal terms, the span geometry of neural networks of integers. And I'm also like this about analyzing some nice properties of neural networks. So the question aligns well in the direction of the optimizer. Very interesting. So I hope I'm gonna see you order into it. Thank you again. Thank you.